All right, tank example number 2 here. This is one where we get a volume that is not constant. In the first example, I think the volume was a constant 100 liters, so that actually made it a little bit easier. There are different things that I can actually change up on these. Come on, man. Oh, come on. All right. There are different things that I can change up on these that will make it so that it kind of increases the complexity. That first one that I gave you was kind of a base level one. The ones that we will sort of focus on will be ones that have a changing volume. So in this case, let's draw our little tank. A little water there. I'm going to say that this thing starts with 50 liters in it. And initially, the concentration is 1 gallon per liter. Come on, man. 1 gram per liter. All right, so then what I have flowing out is 4 liters per minute. Coming in, remember the last time we had the same flow rate on each of them. So instead, I'm going to put this at 5 liters per minute. And I'm going to make it have a concentration coming in of 8 grams per liter. So you should see that in this one, the volume is not constant. I've got more coming in than going out. I'll talk about that in a moment. But first, I want to talk about how what Q really is, because you might need a little bit of clarification after the last video. It is the total, this word's kind of important, amount of salt in the solution in the tank, measured in grams. So I think that the word total helps make sense of it. It's not like how much salt is coming out. It's the total amount of salt in this fluid that we have here. So that may help you see it a little bit better. So let's talk about, since we're talking about what Q is, let's figure out what Q of 0 is, because I'm going to use that to figure out what my C value is. Well, let's see. I have 50 liters and an initial concentration of 1 gram for every liter. So, you might see it. It is 50 liters times 1 gram per every 1 liter. Liters cancel, give me 50 grams. So that's Q of 0. We'll use it later to find our C value. Now what we need to do is look at the volume and how it's changing. So I'm going to write some stuff. Volume of the volume of water, the water in the tank is not constant, since 5 liters per minute, I'm going to not use a complete sentence. It's coming in, so 5 liters per minute in, and 4 liters per minute out. The volume, how does it change? How does it change over time? Well, if I have 5 liters in and 4 liters out every minute, then the net difference between that 5 and that 4 is 1, right? So the volume increases by 1 liter every minute. So notice that's a constant increase of 1 liter every minute. And remember, it starts with 50 liters. So I drew a tank that, like, just say it's big enough to hold a lot of water and it's not going to overflow. So I've got 50 liters here, and 1 liter is adding every minute. So generally what you want to do when you recognize that the in and the out rate aren't the same is you want to figure out an equation for that volume. In this case, it starts at 50, and then I add, it's just plus t, because t measures the minutes, and for every minute that passes, I get 1 more liter. So the volume is the initial amount plus the difference, 1, times the difference in the rates times time. Now this is one where I've got a constant rate in and a constant rate out, so it's not this rate of 1 is not changing. Anyway, so that volume is 50 plus t. I'm going to put a little box around that because that's important. We're going to use that later. Say, for example, this was 6 and that was 4, right? Well, it would change some of the ideas, like that would change this to a 6. This would change to a 4. And if the volume is increasing by it would be 2 liters every minute. So it would have 50 plus 2t. Say I started with no water or no fluid in this tank. It was empty. And I started pouring water in, and then there was just a constant outflow of 4. So it was coming in at 50, out at 4, but started with a volume 0. Then the volume would just be a t. So it would be just, instead of the 50 plus t, it would be a t. So I'll throw different scenarios like that at you. So you have to be really careful and take a look at all of the different rates as they show up in front of you. Okay, so I'm going to pause for a moment. Okay, I'm going to work and I'm going to do the dq dt. What are the units of dq dt? It's grams per minute, because that is Q's measured in grams, right? We should be cool with that. Total amount measured in grams, and time is measured in minutes, is equal to, remember we always do in rates, and by in rate I mean in grams per minute rate, minus out rates. Now I'm going to give you a little bit more of a formula here. What I do here, whoops, come on, man. I take the in concentration, sorry, I'm not going to say concentration first. I take the in flow rate times the in concentration. That is my entire in rate in terms of grams per minute. And then my out, it's going to be a little bit more complicated. It's always the out flow rate times a fraction. Now this fraction is the total amount in grams or pounds if you're using other units, which that's always going to be Q. And then over the volume of the water in the tank. And this can be changing like it is in this example. Now, this fraction right here is pretty much equivalent to this, except for it's out. What is that fraction? It's amount in grams over volume in liters. So this is really just the out concentration. But what I want you to see is the in concentration is generally easier to find because it's given to us, 8 grams per liter. On the way out, it's mixing. It's dependent on how much is coming in. It's dependent on how much time has passed because, it's got a lot more to it So generally this outside is more complicated to find, but it's really just finding the out concentration. I think you're always, when you set these up like this, going to have Q of t in the top of this fraction. You just have to be really careful about what you put in the bottom. Hopefully that helps you a little bit as you're working through these problems. Let me do it for this example. So dq, I'm going to move it down just a little bit. Come on. Okay. All right. Sorry. There we go. All right, so dq dt, grams per minute, is equal to, all right, in flow rate. Well, that is 5 liters per minute. 5, I always write my units. I write these units and I write these units, and I'm always double checking to make sure that they will cancel correctly so I don't screw something up. That'll also help you if you down the line have to do this. Wait, how do I do these? Oh, I figure out the units. All right, I can do this. dq dt, dot, dot, dot. All right, so 8 grams per liter. Now look, liters cancel, gives me grams per minute. Good, that's what I want. Minus, all right, outflow rate is 4 liters per minute times, all right, let's see, what do we have here? Amount is Q, grams per volume. Oh, we just figured out the volume is 50 plus T. So 50 plus T. Now, this is where those cancel, and it does give me grams per minute, just like this one gives me grams per minute. If you don't get that volume equation right, you may think when you cancel this stuff, you cancel the liters. All right, we're good. Like say I didn't recognize that I had a T there. I just wrote the 50, and I would cross this out, right? Like that, cancels with that. Okay, let's go, right? That's an easy spot to make a mistake, and that's a spot where people frequently make mistakes. That's the setup. That's the in rate minus the out rate. Now that we've checked everything, let's write Q prime equals, that gives me 40, 5 times 8, minus 4 over 50 plus T times Q. So let me move it over, and it'll be in a normalized form. Q prime plus 4 over 50 plus T times Q is equal to 40. All right, and I'm going to stop here for this video, and we will pick this up in the next one. I'll fully solve this. Oh, I totally forgot to, I had 2 questions that I was going to pose. That's okay. I will pose them in the next video.